So this is 5.4, number 71. So the first question asks, estimate the zeros of the graph. What is a zero? A zero is when a function equals 0. Therefore, it's called a zero. So when is it going to be equal to 0? In other words, what values of x will make this equal to 0? Well, the first obvious one is 0. Why did I circle that? I didn't want to do that. Okay. Whoa. Okay, try it again. Clearly, 0 works because what's the integral from 0 to 0? 0. Because the area under the curve, if it has no area underneath because you're starting and ending in the same place, it's going to be 0. So the first answer would be x equals 0 would be a 0. Now, where else does that happen? There's another place. So what does this function do? It gives you the net area starting at 0. So let me do this in red. So the area of that piece right there, so if I integrate from here and I stop there, my answer is going to be negative that area. Okay? Now, how do I get back to 0? I have to add stuff. So I have to add an equal amount of area to get back to 0. Where does that happen? Well, you're just going to guess because it wants you to guess. So at some point, the blue area on top is going to equal the pink area below. So it's going to be at that value where the net area will be 0. So when you integrate from here to here, it looks like it's going to be about 0 because that minus that will be 0. So I'm going to guess about 3. At 3, it's going to equal 0. So those are my two zeros. Okay. Part B, estimate, if any, at which A has a local max or local min. This is beautiful. Watch this. Local max, local min. So brain, let's think. So as your function goes, it keeps on getting a bigger and bigger negative. It's decreasing. So you know what? I'm going to do part C first, and then I'll do part B because I think it'll be easier to see that way until I explain it a second way. When it says estimate the points, I'll explain it a second way how to do that. Okay. No, I'm going to explain this. I'm going to do the right way. I'm going to do the right way. What's the justification for a local maximum? You should say when the derivative changes from negative or positive to negative. And what's the justification for a local minimum? When the derivative changes from negative to positive. So the question is, what is the derivative of A? What's the derivative of this function? Here's where the other fundamental theorem of calculus comes into play. So you learned the derivative of an integral from a constant to x, you just plug x in there if you're taking the derivative of that. So this is going to be f of x. So in other words, this function is a prime of x. Huge. That is a very common type of thing on FRQs. You take the derivative of an integral from a constant to x, you just plug x in. So this is the function of the derivative of A. Is there any point where it changes from positive to negative? I say yes. Derivative is positive there, it's negative there. So it's going to be right there, which is what, 8.5-ish? I'm guessing 8.5. And then what's the justification for a local min? When the derivative changes from negative to positive. But this function is the derivative, and it's negative here and positive there. So what's that? That's going to be like 1.5-ish, I'm guessing. So those are my best guesses for local max and mins. And then the last part C wants us to sketch the graph. Well, the area from here to here is 0. If I start at 0 and it's 0, the area is 0. So to graph that, I start here. Then as I integrate, I get the net area. But look at that. The area down there is negative. I'm going to subtract that. So it's going to start to decrease. And then I'm going to subtract more and I'm going to subtract more. But the other thing to notice, at first I subtract a bigger area. Then I subtract less. Then I subtract even less. So at first, the net area is going to really decrease, but then it's going to slow down. Because here, I'm only adding a tiny little negative piece. Then when I get to the right side here, also I'm adding area. It's going to start to increase there. At first, I add a little bit, and I add more, and I add even more, and I add even more, and I add a really, so what you'll notice, I keep adding a bigger piece. So it's going to increase faster and faster and faster up to this point. So it's going to slowly increase. Also, it's going to increase fast. Whoa, why did it do that? At first, it's going to increase slowly and then faster and faster and faster when I get to that point. But after this point, look, I added a big chunk, right? Then I add a smaller chunk, a smaller chunk, a smaller chunk, and even smaller. So at first, it's going to grow or decrease, or excuse me, increase a lot, and then it's going to slow down. So first, it's going to increase a lot, but then it's going to slow down when I get to here. And when I get to this point, I start to subtract these pieces because net area, if it's below, you subtract. So first I subtract small, then bigger, then bigger. So at first I decrease slowly, but then bigger and bigger and bigger. So that is my rough guess of the graph of the derivative of f, or the area function, which is the antiderivative. So let me squeeze down. So this is this pink graph. It's an integral. And remember when we took the derivative of x cubed, it became x squared? Well, this looks like an x squared, so the antiderivative should look like an x cubed, which that kind of does. So that's number 71.